Guys hear me? Yes? How about in the Chibros in the back? Yeah? Okay. Okay, good afternoon, everybody. Welcome to the Grand Rounds. It's my distinct pleasure to introduce today's speaker, Professor Davey Smith, who is coming to us from the University of Bristol. And in epidemiology, we have the privilege of hosting him this week as a professor in residence. So a little bit about Professor Davey Smith. Professor Davey Smith was a member of the noise terrorism outfit Scum Auxiliary in the early 1980s. Since artistic and commercial success eluded them, he has had to earn his living working as an epidemiologist in the provinces ever since. Now, out of this pitiful destiny grew quite a successful epidemiology career. Professor Davey Smith started out as a physician and adopted epidemiology to his repertoire later. He is a preeminent scholar in social epidemiology, and he is one of the founding fathers of Mendelian randomization, which is one of his claims to fame. He also, until recently, was the editor of the International Journal of Epidemiology and led it to new heights of an incredible impact factor of almost 10, right? 11, sorry. 11. Which for an epidemiology journal is unheard of. I should have known, right? I was an associate editor for 16 years myself there. He is actually going to talk to us about modern epidemiology today, which is obviously a timely topic, and I'm curious to hear what he has to say. So thank you so much, George, for joining us today.
So thanks very much for that very kind introduction, and it's a genuine pleasure to be here in LA for this week. My talk today is based on a paper that I wrote at the invitation of the American Journal of Epidemiology, even though that's the competition. But it was a collection that was to mark. I think it's 45 years of SER, or there was some celebration, and they asked for papers that sort of reflected on the sort of situation of epidemiology, and I can highly recommend the issue is out, and this is the editorial for it, and I can highly recommend the issue. In particular, there's a fantastic paper by Sam Harper on the future of observational epidemiology. There's papers by Maria Glymore and there's two by Catherine, by Kerry Keyes. You won't find mine in it because I was so late with the proofs that mine didn't actually appear. But they are going to publish it. I reflected on modern epidemiology, but thinking really of the rise of what became the sort of modern epidemiology school around the crystallization of methods in the sort of 70s when the methodological bases, I think, for what we now consider to be epidemiology were laid down. But I'm going to start by sort of reflecting on maybe what it might be considered pre-modern epidemiology. And here I have to declare a conflict of interest because what I'm going to briefly discuss a now I'm sure forgotten textbook, but the first textbook of non-communicable disease epidemiology that was written by Jerry Morris and published in 1957. And Jerry was my mentor. He was I did an MD which means that it's different in the UK than in the States. An MD is a 3-year full PhD length thesis that doctors, physicians used to do. I don't think anyone does them anymore. It's a useless degree because people, when you try, if you apply for a job in the States, they say anyone's got an, every doctor's got an MD. You say, I spent 3 fucking years on this, but useless degree. But Jerry was my supervisor. He didn't even have like full official supervisors. And his textbook was really had a huge impact on me when I was getting into epidemiology. They were later editions. I think 75 was the last edition. But looking back at at epidemiology, this is the time when communicable disease epidemiology had shifted to thinking that non-communicable disease was the major focus, going to be the major focus for the future of epidemiology in high-income countries. And he identified sort of 7 uses of epidemiology, starting with understanding historical trends in disease, community diagnosis, i.e. just levels of disease in populations, epidemiology to be applied to the workings of health services, then the individual's risk of disease. This is about prediction, but then completing the clinical picture, looking at the full consequences of particular diseases. That epidemiology was actually required for identifying syndromes, including, for example, you might think sort of syndromes around ischemic heart disease and ischemic stroke and ischemic peripheral vascular disease having some sort of underlying process. But by far the largest chunk of the book was the search for causes, was etiological epidemiology, which is what I'm now going to talk about. But as I say, he emphasized the fact that that epidemiology started actually with populations, and it started with trends of disease in populations. And the striking thing that was happening in the 1950s at the time when Jerry was writing this book was that what had appeared to be long-term improvements in health of the population, and this is in the UK, but the same could be said for the US and for other many other high-income countries. There had been this rather dramatic stalling of life expectancy and of falling mortality in males, whereas in women mortality rates continued to fall. So something clearly just sort of happened, and for a non-communicable disease epidemiologist, working out what this was at a causal level was clearly important. And the book is just full of looking at disease trends. I mean, this is for coronary heart disease and demonstrating that this wasn't purely diagnostic. Similar figures were shown for what was a major issue at the then was peptic ulcer, which in the US and in the UK had shown absolutely dramatic increases in peptic ulcer, including deaths through hemorrhaging ulcers becoming reasonably common. And these were the issues for which etiological understanding was necessary, as well as, of course, lung cancer and some other conditions. Indeed, here Jerry subtracted the coronary heart disease and lung cancer from the data and showed, as you can see on the right, that the rates in the males, if you removed lung cancer and coronary heart disease, for which there had been big increases and a huge male excess, this sort of suggested that maybe the major contributor to this stagnation was lung cancer and coronary heart disease. And the community diagnosis aspects, and this is something that I spent a fair amount of time on, that Jerry was interested in was social inequalities, or the differences in health between social groups, but pointing out that those differences in health could be very informative about the causal factors which were driving these diseases. Jerry became sort of famous in the UK in the UK anyway, he was known as the man who invented exercise, because he carried out ingenious epidemiological studies of the contribution of exercise to risk of coronary heart disease. And he famously compared coronary heart disease rates in bus drivers and in bus conductors. In those long forgotten days, the bus conductors would be running up and down the stairs of these buses hundreds of times a day, whereas bus drivers would be sitting down, demonstrating that sort of record linkage and ingenuity existed then. This is a bus conductor from the UK at that time in the uniform. And Jerry did the most wonderful record linkage study, which was you were given your uniform, so it was your uniforms are passed out to you, and he went and they it wasn't digitalized. they got the data from the records, and they got the uniform size, so they could actually get waist measurements and some estimates of height on these bus conductors, and then could actually stratify the analyses to show that it wasn't just that the bus conductors were thinner than the bus drivers. And his studies were just remarkable examples of what we'd now call mixed method studies. So on the one hand, one of the things they did was that they spend a lot of time in what would now be called focus groups, based around the unions, the trade unions, of which all the bus drivers and all the conductors would be in, and they used these to test out hypotheses. And one of the hypotheses was that because the bus drivers were having more coronary heart disease than the bus conductors, and one hypothesis was that it was the stress of driving through London, which was rather less stressful in the 1950s than it is now. So in these groups they would discuss this, and it was unequivocally stated that dealing with the public as a conductor was vastly more stressful than driving a bus. So on the one hand there was that sort of research going on, and then on the other hand he was a dramatically early adopter of methods. And this paper in 1966, of which the remarkable statistician Martin Gardner was his sort of first job, was working with Jerry, one of the leading medical statisticians of all time, in my view. They conducted a multivariate analysis of the predictors of coronary heart disease. And they said, we adopted the method of linear discriminant function analysis, Fisher 1936, Cornfield 1962. So Jerome Cornfield had introduced this in just a purely in a methodological paper, but using Framingham data, but it was a statistical methods paper in Federation Proceedings in 1962. Cornfield hadn't referenced Fisher, who actually developed discriminant analysis, and this is the first application of this method in a paper which is explicitly an applied paper. The famous paper you'll see quoted, Cannell, Truitt and Cornfield, 1967, always quoted as the first multiple logistic regression paper, wasn't, and multiple discriminant analysis, assuming normality, is exactly the same as multiple logistic regression. So Jerry was simultaneously did multiple methods and was also a very early adopter of such approaches when they were seen to be useful. Now this is important because I'm going to go on to talk about old men complaining how things aren't as good as they used to be, which I'm sure is the situation that I'm now in, that I'm now one of these old men complaining about how things ain't as good as they used to be. But the sort of old men in epidemiology, and it was generally men, were quickly uncomfortable with the way that epidemiology was becoming a discipline, of applied, complicated statistical methods, of which multiple logistic regression was the illustrative case. And here's the psychiatric epidemiologist Edmund Murphy talking in 1978, says multivariate analysis, which in certain quarters is being substituted for scientific perception, can spread its soporific effect. And that with respect to some analyses, I'm driven to believe that however excellent the prediction, the formula from an etiological and ontological standpoint provides no insights whatsoever. Or here's Stallone's talking about epidemiology, showing a continuing concern for methods and especially the dissection of the risk assessment that would do credit to a Talmudic scholar and that threatens at times to bury all that is good and beautiful in epidemiology under an avalanche of mathematical trivia and neologisms. And Abe Lilienfeld, perhaps the most dangerous aspect of the state of our discipline today is that there is an unhealthy emphasis on how one conducts an epidemiologic study and not why and what one does in such a study. Simply put, we are training technocrats. So, methods are always, seen to be challenging by those who haven't been trained in them. Now, in the around that time, in the sort of mid-1970s, really the sort of foundations, as I say, of what we would now consider to be modern epidemiological methods were being developed. In particular, two most particular important contributors were Olli Miettinen and Ken Rothman, both from Harvard. And some of the things which now you're being taught epidemiology would just be considered of straightforward concepts like the components of the crude vis ratio and what is confounding. These sort of fundamental questions were being asked about what these things were, even though the terms were being used. They were used in a way for which there was not any sort of foundational definition or foundational description. And in the AJE, one of Miettinen's papers was reprinted. They did a supplementary issue to the one that I failed to contribute to on the history of some reprinting some classic articles with commentaries, and Ken Rothman commented on a Miettinen paper when case control studies, when we actually started theorizing what a case control study was. They were sort of being done, but they weren't theorized. Now, and Ken Rothman, of course, was probably the major contributor to this in papers that I'm sure, I hope, are still being read, such as his paper on causes, on defining basic concepts of interaction, synergy, antagonism, induction latent periods, choice of statistical models, and then on interactions. And when looking at interactions, for example, again, causality was central to what was being considered. So it was stated that the biologic interaction, and this is, you'll all know of this term biologic interaction, that it, i.e. things that are above additive, but called biologic, would provide clues to the behavior of the causal mechanisms involved. So the term biologic attached to this was this notion that this would actually, having this understanding of interaction, would actually provide evidence as to causes. Now, we can get back to at the end to whether this actually happened. And then in 1986, Rothman's textbook, the first edition of Modern Epidemiology, appeared. Now, this was a really expensive book, and I was in the last year of my master's at London School of Hygiene, so I borrowed David Leon's copy, and I photocopied it. So that was but that's my pirated copy, which is just full of all the way through. It's full of these sort of marginal notes, which just demonstrates that I learned a hell of a lot that I hadn't come across before that. And really worryingly, some of my marginal notes have just got some of the formula written down and things I didn't necessarily agree with, and I can't work out. I can't now understand. Obviously, I had a greater understanding then than I do now, because I can't work backwards to realise what I was writing about. But so it had a big impact on the field. But the elders in epidemiology carried on complaining. There's a lovely paper by Diana Petiti in 1988, when she said, she found less and less evidence of scientific creativity and more striking deficits in the understanding of biology. So, so biology had sort of entered, biologic interaction entered, but it was entirely as a statistical concept. And what Diana was saying, and lots of other people, was that actually a genuine engagement with biology was actually falling out of epidemiology. And she went on that the epidemiological literature was becoming an archive of the results of information derived from mechanical applications of multivariate analyses. Now, of course, the developments since modern epidemiology, in the formal languages of causal inference, has sort of transformed our understanding, but is the equivalent really of the sort of the modern epidemiology revolution as it was from the mid-70s to mid-80s. And Jerry, who we saw, so we saw that Jerry was a very early adopter of these multivariate methods when they were thought to be appropriate, but he had the same. He made similar comments. He said, "I share Elwood's." There's a book review of modern epidemiology in one of the epidemiology journals. I share his high regard for Rothman's modern epidemiology, and I'm at present treating myself to a refresher course on it, much reassured in the process by the author's confidence in my statistical capability. However, as a guide to modern epidemiology, the book has serious limitations. And I can vouch for the fact that this was true. He was reading it because he'd come and ask me about, so some of my scribbles were desperately trying to work out some formulae for Jerry to go through it, because he worked his way through it. But, he thought that it was a book that had sort of moved, and you've got to go back to look at the first edition, where there's none of the chapters on substantive issues that appeared in the later editions were there. The first edition was entirely methodological, that it was moving epidemiology away from a concern with health in the populations, and that people wouldn't understand that epidemiology is the basic science of public health, in close on 150 years of epidemiological research, and Dr. Rothman doesn't have much time for history. It continues plausible that the main determinants of the health of populations and sizable subgroups in them are the economic, social, cultural conditions. The data on this are mostly cross-sectional and inevitably derived from studies of populations and groups as the unit, rather than from aggregation of individuals with their various attributes. So, thinking that the sort of micro level methodologies were obviously necessary and very valuable for the research, but should be combined with retaining a focus on populations. Now, this is from the 1976 paper. I'm going to just run through, two or three things that maybe illustrate the implications of maybe forgetting broader biology and forgetting the broader lessons from populations. This is the modern epidemiology expanded upon the causal pies, as it's generally known, the causal pies model of disease etiology, which is an explicitly deterministic model of disease events, and it's deterministic at an individual level. And this is from modern epidemiology, discussing why one chooses deterministic models. It's stated that in our ignorance of these hidden causal components, the best we can do in assessing risk is to assign the average value to everyone exposed to a given pattern of known causal risk indicators. So that's a poor second. Using averages is a poor second. And that as knowledge expands, the risk estimates assigned to people will approach one of the extreme values, 0 or unity. So that our inability to have perfect explanation is epistemological. It's entirely, we could learn it. We could learn, and we will advance to do so. Now, I mean, the epitome of this in current, medical thinking is obviously personalized medicine. I mean, this is the idea that you really could have, a complete understanding if you get over those epistemological problems. And this is a well-known paper by Schork and commenting Schork in Nature, focusing with the usual sort of personalized medicine idea that we're just wasting time, treating a lot of people, because if you do the sort of calculations, you come up with these, in my view, utterly spurious notions that you can actually say that you treat so many people and only a very small number of them benefit. And if we actually knew the predictors of who would benefit, we could just treat them. And I'll actually skip those two. Actually, no, look. So, I mean, an example of the fact that sort of clever people can be led to say ludicrous things on this basis is this sort of commentary on a paper saying that randomized trials aren't the solution because they only give you average chances, and heterogeneity of treatment responses are huge, which is a questionable argument for many treatments. And in that they state statins are effective in lowering cholesterol for as few as 1 in 50 individuals. So this is the idea that you give someone a statin and only 1 in 50 has their cholesterol lowered. Well, seeing as a statin lowers people's cholesterol by about 20%, that means for one person, only 1 in 50 people is the statin effective in lowering their cholesterol. One person, their cholesterol must go to minus 10,000 to actually produce the average effect across the group. I mean, the sort of statements are ludicrous. So, and in many other fields, the notion of cause and the balance between the deterministic and the stochastic models were well developed, in particular in genetics. And in genetics, cause was considered in terms of an underlying liability. So the factors, genetic factors, environmental factors, etc., all come together to influence what might be considered like a normally distributed liability to disease. Famously, in a classic paper by Faulkner, which started a massive industry in discussing liabilities. And analyses in genetics to this day are based upon the assumption of a continuously underlying liability. Now, in the liabilities discussed by Faulkner, three, as in this diagram here, you have a sort of normal distribution of liability, and then you have this sharp threshold above which people get disease. So this is the equivalent of a deterministic model. But in genetics, of course, you have this notion of three, in quantitative genetics, of three components of the variance, one of which is genetic, then one of which is shared environment. So that would be the environment which makes people living in the same households alike, tangible environment. And then the third component is the non-shared environment. Now, the problem with this dissection isn't in terms of how it's done. It can be done in many different ways, not just in twin studies, in family pedigrees. You can do dissection by combining pedigrees and genotype data, etc., and you get the same answers. The problem is that non-shared environment is not environment in any way that it is sensible to use the term environment. Non-shared environment would include somatic mutations occurring during fetal development, non-random, non-equal, which will always exist, cytoplasmic non-sharing during cell division, mitotically stable epigenetic changes, right the way through the whole host of stochastic events, including stochastic events at the biographical level. So you can have a deterministic model when that includes these stochastic events, which you cannot discipline. And in fact, in genetics, that was made absolutely explicit by an alternative set of models which were probabilistic, which just looked at the genetic liability and then said, as your risk increased, then the probability, so you see on the right here, it's just that the probability of transitioning to disease increases as your liability increases. So if you have a higher liability, you're more likely to develop disease, but it is a completely and explicitly non-deterministic model. Now we have a large amount of data which lead us to know, not to consider, but to absolutely know that there are completely non-disciplinable processes that lead to disease risk that we are fantasists if we think we can ever measure. So just consider bilateral organs and tumours in bilateral organs. You know, breast cancer, kidney cancer. You know, the kidney, your two kidneys have exactly the same germline genome. That's what they get. If you eat unhealthy food or eat healthy food, if you smoke, if you drink alcohol, if you go jogging, if you take tablets, whatever, they are going to influence both kidneys in the same way. Any exposure you could sensibly measure except being x-rayed on one side, which, let's face it, isn't a major determinant of these diseases in the population, is going to influence both kidneys. When you develop a parenchymal tumour on one kidney, your opposite kidney has had identical exposure, except for stochastic events. Identical exposure. And yet the risk, once you develop cancer in one kidney, the risk of the kidney of the other side developing cancer over now long follow-up periods, because people live a long, long time now after treatment, is a bit elevated over the general population, but not much. And that has had absolutely identical exposure patterns. So, you know, in these causal pies, you have everything that you could ever measure. Everything you could ever measure is the same. And yet, you get huge differences in revealed disease risk. Now, it is obviously not going to be the case that somehow bilateral organs are different to unilateral organs. You know, the same, you just can't see this for organs that aren't bilateral. But this just tells us the huge importance of stochasticity in disease risk. Now, there's evidence from non-human sources that make this absolutely clear, and biologists would make it obvious. I mean, these are clonal marble crayfish. They're clonal. They're genetically identical. They've been brought up in exactly the same environment. When you go to C. elegans, people have actually done experiments where they homogenize the fluid they're in to take account of any excretion. So it's not even their excretion can't influence their environment. And they have a huge range of life expectancy. They've got the same genes, exactly the same environment. Imagine you're a life course epidemiologist, watching these three and trying to work out why one of them's got big. You're not going to do it. Or to take a human example, here's Winnie. So Winnie has been smoking for 93 years. She's lighting a cigarette from her 100th birthday cake candle, and she's not going to give up now, she says. Now, what you imagine is, so people say genes, well, there'll be a small contribution of genes to this. But you just imagine, when she was 63 years old, say, the postman came at 11 a.m., knocks on the door, opens the door, gust of wind, and she coughs. Metaplastic cell gets displaced. Postman came at 10:59, wouldn't happen. Postman came at 11:01, wouldn't happen. So there will be these events, which, as I say, will range from the molecular right the way through to such biographical events, right the way through, which we could never, ever dissipate. And it seems to me that whilst a stochastic model and a deterministic model mathematically basically give you the same thing, the reason it's important to keep stochastic models in mind is it doesn't lead us into those fantasies of personalised medicine that would follow. It allows us to realise why we're epidemiologists is precisely because of this non-disciplinable risk. So let's do a thought experiment. Okay. Two towns, Bristol, which is where I come from, and Bath. And we'll imagine that everyone in Bristol has to smoke 20 cigarettes a day from adolescence on. So when you wake up in the morning, you're given a pack of 20 fags, and you're not allowed to go to bed until you've smoked right the way down to the bottom, every one of those 20 fags. Now, I chose Bristol for this rather than Bath, because this is what Bristol's famous for, Banksy, the Molotov cocktail throwing teddy bear. Bristol's pretty grungy. In Bath, you see, no one smokes at all. And that's completely believable. If you've ever been to Bath, you won't find many smokers, okay? So no one smokes at all in Bath. And then you follow them up for 50 years. Now, where would have more lung cancer? So Bristol would have more lung cancer. But within Bristol, how does smoking relate to lung cancer risk? What's the association between smoking and lung cancer risk in Bristol? Well, everyone smokes exactly 20 cigarettes a day, so there can't be any relationship between smoking and lung cancer risk in Bristol. So within Bristol, what causes one individual rather than another to get lung cancer? So germline genetics to a degree, but that's, if you look at twin studies, it's not a huge contributor, but it makes some contribution. And then chance events. That's what causes one, maybe some co-exposures, maybe one person's a uranium miner, I don't know. But, it's going to be those sorts of events. But between Bristol and Bath, obviously there'd be vastly higher lung cancer in Bristol, and all those cases are caused by smoking, which at an individual level doesn't relate to lung cancer in either place. No one in Bath smokes. The handful of cases of lung cancer you get aren't related to smoking. So at a population level, an exposure can be responsible for virtually all the cases and not be responsible for cases at the individual level. The individual level, the cause of the cases are chance and genes. Now, I should have learnt this lesson a lot earlier, because in the mid-1980s, the miners' strike was raging in Britain. It's the largest industrial fight there's been the last 100 years in Britain. And if any of you are interested, there's an absolutely brilliant film called Pride, which is out about the lesbian and gays supporting the miners. Amazing film. Go and see it. Anyway, and during that time, I was running an anthropological with two anthropologists. I was involved in an anthropological study of what causes heart disease. So I followed Jerry, Jerry's focus groups. We were going out, doing participant observation, looking at what people caused heart disease. And what I wanted people to say, you shouldn't do a study like that wanting an answer, but I wanted people to say the cause of heart disease was Margaret Thatcher and capitalism, unequivocally. That was what I wanted. But what they said, and here are the papers, inheriting heart trouble. So they said it's constitution, genes. One of the other papers, fatalism, chance. So, and now of course, at an individual level, of course, if only I'd listened to the participants. At an individual level, they're absolutely right. Because, they were observing people, their Uncle Norman lived to 95 and he smoked and drank and, and Harry, a healthy guy, dropped dead jogging around the closed mine, So what people observe are, of course, what relate to individual risk, not what is actually driving the level of disease in the population. And the reason, I've gone on a bit long about this, but the reason why we've got to remember that epidemiology is about probabilities, and is that personalized medicine has absolute limits to what it can do. There's a lovely piece for the statistical side of this. Read Stephen Sen's piece recently in Comment in Nature. You see all these papers which is like the sort of tree pattern overlap. Where you see people who show no response and people who respond to a drug, but very few of them actually test again the second time to see what happens if you then test the ones that don't respond. And what you see is the chance of responding is probabilistic, and it just changes over time. It's a non-stable attribute. But we should be pleased because that actually gives us the logic for why we do epidemiology. Now, in modern epidemiology, epidemiology was then seen to be increasing in status, and Rothman said that this increase in status stems in large part from the emergence of a clearer understanding of the epidemiologic concepts that have become the basis of modern epidemiology. So the status was improving, and the reasons for this was, he says, epidemiology has established a toehold as a scientific discipline, whereas epidemiologic results were once greeted mainly with skepticism. They're now generally accorded some degree of respect. Mid-century epidemiologists had trouble persuading the scientific community of a relation between smoking and lung cancer. By 1984, the situation changed so much that a weak epidemiological association between beta-carotene and cancer occurrence was the stimulus of a biochemical hypothesis on antioxidants. Published in Science, the paper begins with the observation that ecological studies have declared to be respectability evinced by this integration of epidemiology into the fold of the biological sciences stems in large part from the emergence of a clearer understanding of the epidemiologic concepts that have become the basis of modern epidemiology. Now, the older people, there's hardly any older people here, but the older people here will know that the irony of this was that this came just before the largest collapse in respectability of epidemiology there's been, as randomized trial after randomized trial demonstrated that all these factors that were epidemiological studies had said increased or decreased the risk of cancer, beta-carotene, vitamin E, hormone replacement therapy for coronary heart disease, vitamin C, selenium and prostate cancer, etc. All of these things, randomized trials were done based on epidemiological findings and showed no benefit. And then papers appeared like the limitations of epidemiology by Taubes in Science, etc. So that's the third edition of modern epidemiology there. But then Sander Greenland, my mate Sander Greenland, if he was here, I'd still say this. And she was laughing at this. I showed him this. The second edition of modern epidemiology came out with Sander as a co-editor, but the first chapter stayed the same, except rather than the emergence of epidemiology, that's titled The Emergence of Modern Epidemiology, but it gained another author, and there was only one change to it. Can you guess what the change was? They simply deleted this paragraph. That was simply deleted from the introduction. Anyway. Now, the third thing, I realise I haven't got long left, so I will stop. But the third issue which I raise is something where I think, with its amazing advances in terms of methodology, was perhaps a walk back, was this denigration of what were called Bradford Hill criteria. I mean, firstly, Bradford Hill never could. I mean, hands up who's read Bradford Hill's paper? Has anyone read Bradford Hill 96 paper? Do you get taught it, or do you not get taught Bradford Hill criteria? You get taught it, okay. But I'm very pleased that you get taught it, because they say Bradford Hill criteria are wrong, useless and misleading, saddled with reservations, and at the same time, in another tradition, which was causal search literature, Peter Sturtes and Reinhold and Schein said epidemiological criteria for causality were an intellectual disgrace, and the level of argument was sometimes more worthy of the literary critics than scientists. And these are the Bradford Hill's criteria for causality, which I'm not going to go through. After this, there's a 3-hour workshop for anyone who's interested on triangulation and causal inference, and we'll touch more on this. And then a recent talk at a big conference on evidence synthesis. Jonathan Stern, I won't say someone, I'll say who it is. Jonathan Stern, well-known statistician, biostatistician. Brilliant textbook, Kirkwood and Stern. Buy it, he'll be pleased. He gave a talk introducing directed acyclic models and the sort of formal methods of causal inference. And these are 2 slides from his talk. He puts this up and he says the great thing now is that you don't need to learn Bradford Hill's criteria because you've got DAGs. This is the sort of view of causality. Now, I look back to when I entered epidemiology. There's lots of questions that were open, like was HDL cholesterol protective against coronary heart disease? Did triglyceride levels increase coronary heart disease? Why was stomach cancer incidence declining? What was the major ecological factor in cervical cancer? Could alcohol protect against coronary heart disease? Was inflammation important in cardiovascular disease? Did antioxidants reduce the risk of cancer? Cardiovascular disease, what caused peptidyl? I'm not making, it's a shame Roger's gone, but he'd be able to say, I'm not making this really was, this was the list, you can look through the journal at the time, these are the sort of top questions in epidemiology. And the fact is that epidemiology, as we think of epidemiology, has made virtually no contribution to any of these. I mean, ironically, of course, many of them turned out to be infectious. It's either randomized controlled trials, or it's genetics, or it's microbiology without epidemiology. So So clearly just strengthening the methodology on its own didn't get the answers we want. So, I mean, one that I was particularly interested in was HDL cholesterol and triglycerides. I said I was in South Wales. I was in South Wales because I was at what was Archie Cochrane's MRC unit. Archie was then by then retired and in the top room. But, and they were setting up a study in Conversely measured with the HDL hypothesis as the top of the list of things that it was being set up for. And there was this argument raised in epidemiology, in clinical epidemiology, about whether higher HDL cholesterol is protective or is because high triglycerides have adverse consequences. And the answer that emerged was that it was triglycerides were just an innocent bystander, and it was high HDL cholesterol that was protective. These emerged from epidemiological studies by some other evidence. And literally over $1 billion was spent on randomized controlled trials to test billions of dollars to test that hypothesis. So it had some effect. But in 1991, Andy Phillips and I, statistician and I, looked at these data and I'll do this, but we demonstrated, we showed that in epidemiological study, the British Regional Heart Study, that Andy would have found HDL cholesterol appeared protective and triglycerides appeared adverse, but when you adjust one for the other, the HDL cholesterol effect is much more robust. So that's the independent effect you get from your multivariate model. That's just inverting it so they're in the same direction. And then we just took some data from pretest reliability studies on triglycerides and HDL cholesterol, and then adjusted to say, let's see what measurement error has correlation to 0.7 for triglycerides and 0.9 for HDL cholesterol, what would happen. And what you see, what happens is that, of course, if you correct for measurement error, effects increase. For the univariate case and multivariate case, with that level of measurement and precision, it's very clear triglycerides are measured with more error. They go up and down after you eat it, essentially. You got basically the same answer that HDL cholesterol had a stronger effect. You change that from 0.7 to 0.65, and the situation completely flips. So with a tiny difference in assumed measurement error, now it's the triglycerides that appear the stronger effect, not HDL cholesterol. And then you change the 0.9 to 0.95 and it flips back. They just completely resonate. Billions of dollars were spent testing testing the HDL cholesterol hypothesis. I was registered, because I was the MD, which I got in. As I said, the MD was a useless degree, even though I did 3 years of work. So I registered for PhD, studying whether fibrinogen mediated between stress and coronary heart disease, and I'd started it. I'd got quite well into it. I gave up my PhD after I'd done this work because I thought you're just studying artifact. You need something to anchor that on. This is just showing that in 2009, studies were showing exactly the same thing, and conclusions of papers in journal were saying current findings suggest that therapy directed at HDL cholesterol as well as non-HDL cholesterol may generate substantial additional benefit. If you don't know, all these trials showed that raising HDL cholesterol had no protective effect on coronary heart disease at all, using a whole variety of different methods. The only epidemiological informed data, which wasn't available at the time, which would have shown this, was using genetic variants related to LDL cholesterol, HDL cholesterol, and triglycerides. You demonstrate that the variants related to LDL cholesterol, related to higher LDL cholesterol, would predict higher coronary heart disease. And you take into account the effects on liver lipids, that remains solid. With HDL cholesterol, on the other hand, using Mendelian randomization, suggests no protective effect, whereas with triglycerides, which is remnant cholesterol, ApoB containing VLDL and other remnant cholesterols is associated with this. So incorporating biology, actual biology, not just naming something as biologic, has some benefits in epidemiology. So the Bradford Hill criteria, I think, are the sorts of bases for evidence synthesis in epidemiology, and that you can demonstrate how applying a whole set of different methods, which all have potential biases, but with orthogonal biases, i.e. the biases in one would not associate in the same direction as the biases in another study, and using a whole variety of different methods it actually gives a firm basis for firmer basis for causal inference. So I was just going to go on. I'm going to go on to. Have I missed the slide? I was going. So here's here are the data from Dole and Hill's 1956 paper on smoking and lung cancer. This is the dose response effect you get from smoking and lung cancer on its own. You know, that's strong evidence. Well, appears to be strong evidence, but was obviously more convincing because of how it fitted with population data. I know I showed that earlier. But also, if you look at these are birth cohorts, these are different birth cohorts smoked, and this in men, and these are the birth cohorts, and the and then that's for women for men, of course, it went up and down, but women started later. Later birth cohorts started and started going down later, and if you look at the lung cancer. Birth by birth just went with the smoking in men and went with the smoking with women. So you combine your individual level data with your population data. That's one of the 8 or 9 things you would triangulate. Now here's a paper. This is a recent paper where all the modern causal inference exposed approaches, led by Tyler Van der Velde in JAMA Internal Medicine. This is a religious service attendant. They didn't give the data for all-cause mortality in the table. I'm too lazy to tabulate it. This shows around twice the effect of smoking on all-cause mortality. This is religious service attendants. So you've got you know you've adjusted for everything. You've done sensitivity analyses, twice the effect. So religious service attendance has twice the causal effect of not smoking. But then you look at population trends. This is the trends in Ireland of religious service attendance. It's gone down from 90% to 40%. If you had that size effect on all-cause mortality, if that was causal, mortality rates in Ireland would not have dropped at the fastest rate they've ever dropped. I mean, you know, if you put those two things together with something which has such an effect and has such a high population prevalence, it's very easy to do the math. Now, I mean, the interesting thing is, you know, there's incredibly clever methods applied to individual level data, but actually putting it in the context of what's going on in populations would give you a different impression. So triangulation, we think, is a good thing. And finally, why criticizing epidemiologists being concerned with social deprivation is, you know, one reason to just be do-gooders, but one reason is that for the is that it was a different social pattern of different conditions. It isn't just that the poor have more of everything. Chronic heart disease, better off people at higher risk. That this can be really helpful for understanding disease etiology, which is what I'm talking about today. As well as for understanding maybe what societies should do. So perhaps epidemiology is now poised to become modern if one remembers population data and integrates the huge power of modern biological data into it. And if you want to hear more, I'm around for a week, so I will be giving some other talks. But sorry I went on for so long. Thanks very much. Cheers. Oh, thank you.
We'll remind you of our department record.
Okay.
Great job.
Thank you.
Mm-hmm.